What you just heard was Chopin's Opus 25 Etude number 12 from the 48th bar to the end, played by a computerized piano. His etude is nicknamed Ocean for its up and down motion the pianist has to play, a reminder of ocean tides and waves. Now this piece is no joke, as it's known to be very difficult to perform properly with the correct phrasing and correct technique that takes years to master. Now I've been a musician literally all of my life, and it all started with me learning the piano at a very young age. This progressed into me learning a multitude of musical instruments, such as the violin, viola, cello, bass, trumpet, French horn, trombone, euphonium, tuba, and a few others. Although I didn't become a prodigal pianist, as I've only taken piano lessons for about a year, the violin stuck out most as my primary instrument, and it still does as I perform in San Diego State University's symphony orchestra. However, I did not major in music as some would think. I instead found interest in science and math. Majoring in music is not an easy thing to do, and I eventually admitted to myself that I did not have the mental capacity to handle the competitive nature of being a musician, nor learn the infamous teachings of music theory. I found more comfort in learning how the universe behaves written in math, rather than learning about how some deaf guy wrote a mopey piece on the piano. But what does this have to do with anything? Well, naturally, as a musician and an undergrad in physics, Chopin's Ocean etude reminded me of the up and down oscillating motion of a photon. Photons are some very interesting things that loves to interact with many things, not limited to electrons. Speaking of electrons, when an incident photon strikes an electron, presumably at rest, the electron is set in motion as recoil, and the photon loses some of its energy to the photon as the wavelength increases. This is known as the Chopin Effect. It's useful to note that the Chopin Effect isn't that significant for photon wavelengths within the visible spectrum. Only wavelengths that are on the magnitude of 10 to the negative 3 nanometers will have an easier detection. Although visible light still behaves in the same way, such as X-rays, the detection of the occurrence of the Chopin Effect is near zero. The quantity lambda c is known as the Chopin wavelength, and delta lambda describes the difference of the photon's wavelength after collision and the photon's initial wavelength before the collision. Chopin himself used an incident photon that has a wavelength equal to 0.071 nanometers, with the ratio delta lambda over lambda equal to 0.03. Given this ratio, the scattered photon is then calculated to have a wavelength 7.313 times 10 to the negative 11 meters. Delta lambda is equal to 2.13 times 10 to the negative 12 meters. Using the Chopin effect formula as shown, the scattered photon leaves the collision at an angle, beta, at 97 degrees. The recoil electron angle, phi, is roughly 40.8 degrees, with the electron having a momentum of 1.38 times 10 to the negative 13 kilogram meter per second. Now, back to the piano piece. Its up and down motion is thought of as having a wavelength equal to one measure. In musical terms, a measure is defined as a section of time dependent on the time signature of the piece. For example, a piece with a 4/4 time signature's measure will have 4 beats per measure. Since we took the piece's wavelength equal to one measure, we took the piece's wavelength and made a collision with an electron. The piece's wavelength after collision will then be longer than the 4/4 time signature. Now, this increase in time is not that significant, as it only increases the wavelength by a 32nd of a bar. For musical selection, I chose an impact point within the piece. However, the period of the wavelength actually becomes 2 measures as written by Chopin, which is perfect because the piece is written as straight 16th notes, its duration twice of the 32nd note that is increase mentioned earlier. So, the piece's time signature then changes to a whopping 33/16 to account for the extra delayed time. Now, I present the newly written Etude Opus 25, number 12, with a musical impact on measure 25, where the period of the wavelength is increased. Thus, the wavelength is increased. I encourage you to listen for the slightest of delay towards the ends of the piece, as it is very small. The Chopin effect has only a relative small collision. After the musical collision, the piece sounds jarring, and it doesn't flow into the next beat as well as it did before. And without further ado, here is the newly written Ocean with an impact.